Okay, this is my second video for my Algebra 3 Prerequisite chapter number 1, in which we're going to discuss what we mean by a set, okay? So let's go ahead and talk about what a set is. We say a set is a collection of objects whose contents can be clearly determined, okay? We often represent sets using Venn diagrams when you talk about things in probability, but we say the objects in a set are called elements of the set, and we give an example here. You'll notice that these are, and it's kind of hard to read, but these are cusps, okay? So one important thing to note here is that we use cusps to indicate a set. We will not use brackets, we will not use parentheses, so these things will not be used. We always use cusps. And you'll notice also this, I'm using counting numbers is what we would call these here, but we say 1, 2, 3, 4, 5, but also that we have this dot, 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 which would indicate that there are members of this set that aren't listed here, but that we can infer what they are, okay? Another convenient way to write a set, as a matter of fact, is using what we call set builder notation. Okay, so in this notation, we say the elements of the set are described but not listed. So for instance here, what I'm writing is this is the set of, it's kind of hard to see again, but I have cusps. This is the set of all x values, where now I put this vertical bar, okay? And what we're going to do on the right side of this bar is we're just going to describe what the x values are. So we say they're all x values given that x is a counting number and it's less than 6, okay? So we could say that the set of that would be just this set here. We could list it out. These are all counting numbers such that they are less than 6. So these two sets would be equivalent sets here. So if A and B are sets, we can form a new set consisting of all elements that are in both A and B. And what we're going to do is we're going to refer to this as the intersection of the two sets, okay? So as a matter of fact, the intersection of two sets is the first place we're going to stop, and it is exactly what we kind of mean it is. If we had a set of elements here, A, and a set of elements, B, the first thing we want to indicate is that we indicate their intersection as A with this upside down U and B. I kind of look at this upside down U, this means the intersection, as I kind of look at it as an A, like an and, okay? But we say the intersection of these two sets is only the elements of the two sets that they have in common. So it is a new set that only contains the elements that they have in common. So the intersection of sets A and B, written as A intersection B, is the set of elements only that they have in common to both A and B at the same time. And if we were to express this in set builder notation, we would say, well, the intersection of A and B is all x values such that x has to be in A and in B. It has to be in both of them. So if we were to look at these two sets here, what I would like to do is find the intersection of these two sets of sets. So let's look at this first one here. We have a set of 3, 4, 5, 6, 7 and a set of 3, 7, 8, 9. Looking at these, we could just circle what they have in common, but we say the intersection of these two sets is a set itself. And we say it is the set containing, well, it looks like 3. They both have 3 in common. They don't both have 4 in common. They don't both have 5 in common, nor do they have 6 in common, but they also shared 7. So if I were to say, well, what is the intersection of these two sets? It is the set containing these two elements, 3 and 7, because that is what is in both of them. Likewise, if we look over here, you might notice, well, the intersection of these two sets, these are even numbers, 2, 4, 6, and these are some even elements here, 3, 5, 7, not all of them. But you'll notice that these have nothing in common. So what I'm going to do is I'm going to write that the intersection of these two sets is really this set right here. And you'll notice that there's nothing in here. We call this the empty set. We also refer to this as the null set, okay? Another way that you will see this written is a circle with a slash through it, okay? So basically it is the set containing no elements because they had nothing in common. We have talked about the intersection of two sets. Now what I want to do is consider the union of two sets. And when you think of union, of course, I think of like the marriage of two things, the putting together of two things. But we say that the union of two sets A and B, we write this as A union B, and you'll notice that we write that U right side up this time, A union B. But we say it's the set of elements that are members of both set A or of set B. It could be of both sets, okay? So the interesting thing is here, it includes anything that is in either A or B. And graphically, you'll notice that I have that A union B down at the bottom, but it's basically anything in both of these sets. It's both of them kind of glued together. So when we say, well, let's determine the intersection of these two sets, I don't want the intersection of these two sets. I do mean to say union here. Let's have these two sets, say set A and set B, and we say, what is their union? Well, A union B would be equal to this set containing all elements of each. So you'll notice that they both have 3 in common. When we write their union, we only need to list 3 once, because once it's in the set, it's really, it's listed for good, and we don't have to list it twice. So it'd be 3, 4, 5, 6, 7. They both have 7, but we're unioning these things together, and we say 8 and 9. Okay, so this would be the marriage of both sets put together. Would be this new set right here. So while we're on the topic of sets, we're going to discuss probably the most important set, but the set of real numbers. And the important thing about this is that we tend to split these sets of numbers up into subsets. Okay, so the set of real numbers is able to be split up into these subsets here that are very, very common. So we're going to visit each of these, starting with the natural numbers. When you hear natural number, these are numbers that occur in nature. We also call these counting numbers. And because we start at 1 and we kind of proceed up to positive infinity, going by integer values or whole number values. So examples of the subset of natural numbers would just be these kind of numbers, maybe like this here or this here. When we talk about the whole numbers, you'll notice the only difference between the natural numbers and the whole numbers is that we say, well, 0 is considered to be a whole number. So we say all non-negative integers. Okay, and that's interesting that I say integers. You've maybe heard this word before, integers, but an integer is kind of like whole numbers, but then we build in the negatives. We say that these are all non-decimal values and they include negatives. Okay, so now we're kind of building up and making these subsets bigger and bigger. Now the set of rational numbers, the interesting thing about rational numbers, we say the root word here is a ratio. And remember that a ratio is something that can be written this way, kind of like division. So we say, using set builder notation, it's any expression a over b where a and b have to both be whole numbers or integers. I don't want to use whole numbers and confuse you. They are both integers, so they can be positive and negative or 0. And notice that the only stipulation here is that b cannot be 0. And the reason why is because we can't divide by 0. So giving some examples over here, you'll notice that negative 17 can be considered an integer because I could also write this as negative 17 over 1. You'll notice that it's also written here. Negative 5 over 1 is also an integer. Any of these over 1 would also be integers. So if you're, say, a whole number, you're also a rational number as well. Another thing to mention about rational numbers is that they are often decimal. So if I said 2 over 5, which is what this is right here, 2/5, it comes out to be 0.4, but what I want to indicate is that it terminates. Okay, a terminating decimal means that it has to be something that is rational. Another way to look at this is we say 2/3, which is what this value is right here. It maybe doesn't terminate, but perhaps it repeats itself indefinitely, okay? So if it repeats itself and it maintains that pattern for good, 0.6666666, the idea here is that it's considered to be rational as well because I could write this as a ratio. And last but not least, we say it's either rational or it's irrational, but we say an irrational number is a set of all numbers whose decimal representations are neither terminating, they can't terminate, nor do they repeat, okay? So irrational numbers can't be expressed as a ratio. I can't do it this way. So these are often seen as, radicals. We say root 2 would be like this number here. You'll notice that it's going to go on forever and ever and not repeat itself. Or pi. Pi is a pretty famous number there, and it's also irrational. So one thing I want to indicate is kind of this epic diagram over here, but we say when you classify numbers, really what we're saying is you're either irrational or rational to begin with. All real numbers are either rational or irrational. Can you write it as a ratio or can you not write it as a ratio? We can often identify this just by looking at the decimal. But you'll notice that the integers fit inside the rationals, and the whole numbers fit inside the integers, and the naturals fit inside the whole numbers, kind of like we're looking at up here. All natural numbers would be considered to be a whole number because whole numbers are 0 plus all the natural numbers. And integers, all whole numbers are considered to be integers because, well, it's 0 up to positive infinity using all whole numbers, but then this builds in the negatives, okay? So what I want to do is consider the following set of numbers here. And what I want to do is I want to list all the numbers that are in the set of natural, whole numbers, integers, rationals, irrationals, and reals. And the first thing I want to do is I want to go through and I say, well, can we identify any that we would consider to be irrational right off the bat? And the two that I can indicate right here that would be irrational would be pi divided by 2, because pi, remember, it doesn't terminate and it doesn't repeat, but also the square root of 10, okay? Now you'll notice that I didn't include the square root of 9, even though irrationals, down here, I'm saying that radicals are included. And the reason why is because the square root of 9, recall, is 3, or 3 over 1. So as far as irrational numbers are concerned, we'd say pi over 2 is considered to be irrational, and so is the square root of 10, okay? So all of these are considered to be real, okay? Let's start with now rational numbers. Which of these could be considered to be rational numbers that aren't irrational? So I'll get those irrational ones out of the way. And what I'm going to notice here is this. We say that negative 9, it could be written as a ratio, negative 9 over 1. Or negative, 1.3, this has a decimal. but it's terminating, okay? So this would also be considered to be a rational number. 0 can also be placed over 1. 0.3 repeating. Well, remember what we said about rational numbers. They can repeat themselves indefinitely. And last but not least, this is also, the square root of 9 is also considered to be a rational number. So any of these, well, you know, -9, -9, -1.3, 0, 0.3 repeating, and also the square root of 9 are considered to be rational. So now let's kind of take it down a little bit further here. We say, well, which of them are integers? Now, integers, recall, have no decimals, but they can be positive, negative, or 0. So which of these up here can I cross off and say is not an integer? Well, anything with a decimal, here, I'm not going to include those in the set of integers. But I notice with the ones that are left, -9 is an integer, 0 is definitely an integer, and then we say that the square root of 9 is an integer because it's really equal to 3. Okay. So now let's boil it down to whole numbers. What is the difference between an integer and a whole number? Well, a whole number is kind of like an integer except for it can't be negative. So carrying these over here, we could say, well, -9 is now out of the running. We say, well, 0 and the square root of 9, we're going to consider those to be whole numbers. And then last but not least, we say, well, in the set of natural numbers, these are the set that start at 1 and go up to infinity, going by whole increments here. We say that, you know, we can't include 0 because 0 is not in the natural numbers, but we say the square root of 9 would be that there. But that is everything you'd want to know about sets. Cheers.